So for number one, it says like as described in class. So I'm assuming that's from example 4 here in this
Let me
page.
see. It's this checklist. So you want to go through this checklist.
Right.
And yeah, so you want this is the one you want to go through. So what you would do.
So it's just like, is this how it's like defined though, or
For number one.
for number one?
Number one, I think this is kind of like R2. Oh, yeah, so I'm looking at number 2. So, yeah, so number 1, you're in Z2, yes.
Which is this, so
Right.
it's like this.
So, like, if you take an arbitrary vector, how do I do this? If you take, like, X, it could be 0, and Y could be 1, like that. And then you would just go through and literally go and check every single one of those possibilities in that checklist.
Okay.
So, for example, is it true if you go to the first one?
X plus Y equals Y plus X.
Okay, so for this case, is it true that X plus Y equals Y plus X?
Yes.
Yeah, because 0 plus 1, evens plus odds is the same thing as odds plus evens.
And these are all, they're like X and Y here are sets, not like.
Yeah, they're entire.
Okay,
It's like the
sets
box
of
of
even
all
odds.
evens and the box of all odds. So if I
Okay.
add them, I gave you a chart of the addition
Right.
chart. So you just go look
Yeah.
down there and you
Okay.
try all possibilities.
With
and
like looking through all these other cases. And stuff.
right.
Okay.
The only one I think people struggled with was this one on the board that because if you read that checklist, it says if I have an equation basically. That there exists a solution for this equation. So now what you're going to do is flex these two. So, for example, I could put 1 here. You have to do all possibilities. And I could put 0 here. Is there something I can fill that blank in with? Go look at your table. Is there
Okay,
anything
so
that I
the
can
1.
add? Yep. So 1. So you'll literally exhaustively check
Okay.
every possibility and show that it works.
Okay. All right. And so do you use? I'm just confused. So this, are we supposed to use like the proof like wiki to do this? Cause
No, remember I told you that one of my physics friends said this is not a real proof.
Okay.
You're just going through the box and going, check, check.
So
I
that's
think he called
for
them show me proofs.
number 2 also is like it's not like okay.
Number 2 is, yeah, you just go through the checklist.
Okay.
I don't know if that's really, I think I agree with him. It's not a real proof. It's like you're going through the
Just
checkbox.
going through the checklist or
It is a proof, but it's
proof
different.
by checklist, I guess.
Yeah.
Yeah. Okay. Okay.
There was a mathematician that tried to write in his paper checkability. And I said, that's not a real word.
Checkability.
Checkability. I said, that's not a word.
Okay. I have a question about like. So I don't understand really what this like F is in the.
It's
in the
so
notes.
there's something called a field, and the field
Okay.
satisfies certain properties.
Okay.
And we're going to get to that when we do the abstract algebra piece.
Okay.
But the real numbers are a field. They're an example of a field.
Right.
And the fields are like, they behave like the real numbers. So in real numbers, you can do all kinds of stuff. That's why you use them.
Yes, ma'am.
You can put equations on them, and in a field, every equation, you can start talking about algebraic solutions to those equations. So in the real numbers, you talk about equations and solving those equations. You have distributive laws. So you have certain properties, checkability properties on that too.
Yes, ma'am.
But you can think of for now F as being R. For Z2 is a field actually.
Okay.
So the scalars could be coming from Z2. And so I just gave you a different vector space over a different field just to show you, hey, I can run through all these items as long as I choose my elements in the field to come from Z2.
Okay. So
The scalars are now Z2.
So F is like just any field that you could choose. So it could be like reals, or it could be like
Z2.
C2 or integers or something like that.
Integers is not a field.
Oh, okay. All right.
But yeah, so the integers fails to satisfy certain things.
Okay. All right.
I can actually show you because that's. I feel like I'm doing a little bit of what's his face is. You kind of have to know something.
Straying or whatever.
Yeah. You have to know it before you take it.
Yes, ma'am.
Math. So this is it has to do with algebra and solving equations.
Oh,
But they should have a
okay.
checkability list here. So you have what you have is addition and subtraction, and you also have division for everything that's not zero.
Oh, okay.
And then it satisfies everything that you can imagine. Real and complex numbers are fields because it satisfies those definitions.
Okay.
I don't. Yeah.
But
So
integers
here's
are-
their checkability.
So
Associativity, and you can mix and match you can do all the stuff you've always done in the real numbers. And you're so used to that there were actually people that kept trying to divide when we were talking about integers. Integers
Right.
are not a field. You can't divide. There is no inverse to multiplication.
Got it.
But on a field, you do have that. And it's closed under these properties. So we would say it's not closed under it's not closed under division because I can take two integers, divide them, and not get an integer anymore.
Right. Yes.
So it's not the integers does not represent a field. The
Okay.
rationals, maybe.
Maybe. Okay.
I could actually we could actually do something over the rationals. I don't think it blows anything.
Because you could still do division with rationals.
Yeah.
Like you just can't have I guess square roots or something.
Right, but that's not square is not a rational, so I'm not going out of the space.
Right.
I'm not leaping out of there.
Okay.
So
I see.
it's closed under that as long as you're not using what we call the additive identity or zero, because you can't invert zero.
Oh, okay.
So everything but zero.
Right. Okay.
So that's what a field is, and so Z2 satisfies that. If you like, it's some would maybe think it's a stupid one, but it satisfies all those things.
Okay. All right. Okay, that makes a lot more sense to me. So for number 2, I was looking through this checklist, and I really can't find anything that talks about scalar multiplication too much. I guess I don't know. It seems
So I
like
think
they're all
I gave
combined
you a list here of scalar multiplication where the lambdas can come from, right here,
Oh, okay.
right? So I can do all scalar multiplications.
Okay.
So if I had, is it true if I have lambda or alpha times beta, like I make two lists here,
Right.
would I get, so if I have, for example, I could make a little table, alpha, beta, x, and then I forgot how they did it. I forgot my checklist.
Alpha plus beta times x.
Okay, so we could, and alpha x, beta x. And you could just check, does it actually do these two match up every time? So I could have here 0, I could have here 0, I could have here 0, I could have here 1, I could have here 1, I could have here 0, and then I could have 1 and 1.
And so you're just checking to make sure these two are the same.
Right.
Okay.
And then I would check all possibilities of x equals 0, and then I'd make another table for x equals 1 and x equals 2. So it's a
Okay.
literal actually there's only two
Right,
tables.
okay.
There's x equals 0 and x equals 1. There's only two things.
Right. Yes, ma'am.
Right, so you have two tables.
Okay.
So if you do this in Word, then you just copy paste.
So alpha and beta aren't just scalars then?
They are scalars. The scalars are coming from Z2.
Oh, they're coming from the set. Okay. Or
Z2 is a field.
Okay, got it.
So my scalars are coming from that. That's why I made that one sheet at the very end like this. See, my lambdas are the elements from Z.
Oh, okay. Because so for number 2, the only property that seems to be different to me is the scalar multiplication, because it's lambda times the vector x.
So
is
so this is number 1.
Okay.
Right, this Z2 thing is number 1. For the other one, if you're looking at number 2, you will go through all those checklist things, and it's going to blow one of them.
Okay, I figured. Yeah, it looked like
It's probably going to blow this one.
Okay, because...
I think if you do... what you can do is go alpha plus beta x.
Oh, because this would be... Because this would be alpha plus beta times x, so it'd be alpha plus beta times x1, and then...
It would be like this.
1 over alpha plus beta times x2.
Right. And so if you did alpha x plus beta x, you probably will not get the same thing.
Right, because it's like, two different parts of this.
And it's because the common denominator thing you won't be able to get.
Okay.
But so I did the...
Because this will be like alpha or 1 over like beta times x2 for like the second part of it, which is going to be different. Yeah, we'll have the common denominator. Okay, right. I see what you're saying. Okay.
And the last one, I told you guys you could actually just run that. So as a CS major, you can just stick that into Python and just, I don't know what you code in, but it's just
works, yeah.
for the pseudocode would look something like this. For
I was just confused
n
by the
equals
notation
1,
number
2.
3 again, because it's like, so are we finding the magnitude or whatever of this sequence?
Right. So so I gave that to you in class in the last lecture.
Okay.
So the last handout that had like 6 slides per.
Okay. Right.
And so you're supposed to really, the magnitude of 1 over n is equal to 1 plus 1/2 squared plus 1/3 cubed. Square, and all under a square root. I gave that to you in class.
So it's a series. Or no. Okay, yeah, because you're finding the magnitude.
Right.
So it is like a series underneath like the square root.
Right. Well, you just square root your answer. So I would do if I was going to do it numerically, I would do a for loop to get my series.
Just let it run for like a long time. Yeah. Okay.
1,000's probably enough. It'll take 2 seconds for it to do it.
Yes, ma'am.
And then you would just initialize your sum equals 0, run a loop. 10,000, and then you already know what converge is because it's in there. I already told you that.
Okay.
And then you would just do sum is equal to. I don't know if you're allowed to do that in Python. Do a re.
Do what?
Do like a reassignment.
Yeah, I think you can. Yeah. So
it starts at 0. This does it like 1, and then it'll be 1 plus 1/2.
Okay,
Actually,
so you just keep adding 1 over n to
squared.
Squared. Okay, and then you just take the square root at the very end of the sum.
Yeah, and then after it, and then go.
Okay.
Print, whatever. I'm like using BASIC or whatever the language, but
yes, ma'am.
you dump it out and it should give you what that series that's what that magnitude is equal to.
Okay, so we're just finding it like numerically then, or are we like seeing like what it's kind of approaching and then we like write that, or we're not.
How do you prove that it's actually approaching something? Well, one way you could do that is you could do a capture. If you look at sequences, when they converge, the elements start to get close to each other. And so the difference between the previous step and the next step should be smaller and smaller and smaller. Should be close to 0, right? So you could say, you could do a while loop. If you want to do it right, do a while loop and tell it to stop when that difference is below epsilon equals 0.01.
Okay. But so we're just like doing this numerically though. It's not. I don't know. It's not.
Yeah.
Okay. I just wanted to.
You can do it analytically if you want to.
Yeah, I'm not sure how.
You can do that like by maybe using recursion. There are people that are really good at doing those things, but I would throw it onto a computer.
Okay. All right. And then
I like to also see it. So one thing you could also do is just have it spit out the data table, and then you can see it.
Okay.
That it's actually converging. You could take the difference in the third column, the sum, the previous sum, and show that that's closing down to 0.
Okay, I see. and then so that would show you that it's converging. Okay.
Yeah.
I don't. So, real quickly, I don't really know what L2 like a reals is.
So
What's
in the
that mean?
last lecture notes, I
Okay.
defined it again, and I defined it, I think, on this one too. I might have, anyways. Yeah, yeah, here it is. This is little L2 of R, but I did it again.
Little L here.
Yeah. It's the sequences such that the square sum converges.
Okay. Okay.
But it's also in the next lecture notes too.
Got it. Okay.
So the elements, the vectors are entire sequences.
Sequence partial sums convergence. Oh, L2. Okay. Yeah. So each vector is the entire sequence?
Yeah.
Okay.
So this is an example of one sequence that's in there. There's a ton of sequences in there, but this is an example of just one vector.
Oh, okay. I see.
Believe it or not, this has a lot to do with Fourier series
Okay.
and Maxwell's equations and things like that that actually have applications.
Oh, wow.
Even like your Fitbits environments, they're all using this little L2, the capital version of it, inside it. So it's unbelievable, but it is. I think Fourier, when he first did his series, he didn't know it was applicable, and he was also kind of a little raw, so he was not accepted into like the elite scholars, and he died not realizing how important it was. And now we use it in almost every technology we have, because we use it to filter out noise.
Okay.
So if I move, if I just go like this, its noise isn't going to record a step. So there's got to be something in there that filters that out, and that's the Butterworth filter, which is based on Fourier series, which is
Oh, wow.
which is coming from this.
Okay. Convergence series, I guess.
Yeah, it is.
Wow. All right. Well, thank you, ma'am. I think that answers about all my questions.
And if you forget